Neuromorphic computing has emerged as a promising avenue towards building the next generation of intelligent computing systems. It has been proposed that memristive devices which exhibit history-dependent conductivity modulation could efficiently represent the synaptic weights in artificial neural networks. However, precise modulation of the device conductance over a wide dynamic range necessary to maintain high network accuracy is proving to be challenging. In this project, we constructed a circuit that emulates the behavior of one building block of this system. This behavior demonstrates that the nonlinear accumulating nature of memristors promotes long-term potentiation or depression synaptic dynamics of memory transitions. This circuit is demonstrably able to validate the fact that varying the presynaptic signal in the signal transition state is highly stochastic and results in a phase of unpredictable fluctuation before becoming a steady action potential lag signal. As you can clearly see, these signals are highly unpredictable, and that's the synaptic transition state. The input of this circuit, or as we call it, the presynaptic signal, is a pulsing light. The first part of this circuit is an inverter Schmidt trigger that produces an amplitude modulated signal, and then that signal goes through these decoupling capacitors in what we usually call differentiator subcircuit. The result is a tiny spiking signal that controls the emitter to collector voltage across the BJT transistor, and from there we get an inverted action potential lag signal that is measured in millivolts. And that's why we need these two op-amps. Just in case you haven't quite noticed, we have a third op-amp that acts as a voltage follower buffer. The output, or the postsynaptic signal, becomes an emitted light that simulates how the memristor should respond to its initial conditions.